Welcome to video 3 on the TTB course. This video marks the start of part 2 of the course. In part 2, from video 3 to video 10, we consider various techniques that form the foundation of reliable TT systems. In this video, we begin to consider the design and implementation of effective tasks for use in TT systems. Our main focus will be on I/O activities. The material in this video is based on Chapter 3 of the ERES2 book. If you haven't yet read Chapter 3, I suggest you stop the video now and read the chapter before continuing. So let's start with a basic introduction. Many embedded systems, of course, have real-time I/O, input-output requirements. These requirements may involve responding to switch presses and other sensor inputs, reading keypad inputs, displaying data on different kinds of display, for example, a graphical LCD, a text-based LCD, receiving and transmitting messages over communication buses. Lots of different protocols are used there. All of these things we need to be able to handle in our system. If it's a TT system, we want to try and avoid using interrupts to support these activities, because use of interrupts would make our system behavior less deterministic. In other words, if we use interrupts and these interrupts can occur at effectively random points in time, makes it much more difficult for us to model the system precisely. And that's what we're trying to do when we create a TT system. So our goal in this video is to talk about some basic I/O techniques and architectures that will allow us to avoid using interrupts in our TT design when we perform I/O activities. So I/O will be our main focus. What we're going to look at in this video is a combination of what's called polled inputs. So polling basically refers to a process whereby we periodically check an input. So for example, we might check a switch every 5 milliseconds or something to see whether the switch is being pressed, rather than trying to connect that switch to some form of interrupt input. So if we poll it, that means periodic checking. We're going to use polled inputs combined with what we'll call a multi-stage task to support I/O activities in our system. This video will also consider ways in which we can employ various forms of software and hardware buffering to allow us to maintain the advantages of a TT architecture, even in situations where the I/O activities involve high-frequency events or large data transfers. So our basic goal is to look at polled inputs combined with a multi-stage task, and sometimes also employing software or hardware buffering. So what do we mean by a multi-stage task? The key to designing such a task is to appreciate that it does not involve waiting. If you've got a delay loop in your task, you're probably doing something wrong. So rather than sitting in a delay loop while a hardware action completes, for example, while we wait for a switch to stop bouncing or we wait for a UART to send some characters, what we do instead is we store the current task state. Rather than waiting, we'll run the task for a while. If there's something that we need to wait for, we'll pause the current task, return control to the scheduler, and come back a few milliseconds later, restore the task state, and carry on from where we left off. If we do it this way, for example, if our task runs every 10 milliseconds, we do some initial activity, we return from the task, we call the task again 10 milliseconds later. In that 10 millisecond gap, some other hardware or other external activities may have taken place, and we then respond to the changes in the overall system state. So the key is Multi-stage tasks involve storing the task state, storing the task state and calling the task periodically, picking up each time we call the task from the previous task state, carrying on, storing a new task state, returning control to the scheduler, running the task again a few milliseconds later, and so on. So we've already looked at one example of a multi-state task, and that was from the video 2 when we looked at our first switch reading task. So this is the switch reading task again. The key to this is up at the top here. We have a static variable, duration S, and this stores the duration of the switch press. What it's counting up here is the duration of the switch press measured in task calls. So the duration increases by 1 if the switch is pressed, if the switch is still pressed after we've called the task once. If it's still pressed after we've called the task 10 times, the duration S will be set to 10. So there's no delay code in this. We're just quickly checking to see what the switch state is. If the switch is pressed, we're incrementing our state variable. We're then checking whether that state variable is greater than a threshold. If it's greater than a threshold, we store the fact that the button is pressed. If the switch has been pressed for some time, is pressed but hasn't yet been pressed for long enough, we set the global variable to button not pressed. If the switch isn't pressed at all, we reset the count. So we reset the static variable value and we update the status. So we're storing the state of the system, we're calling it periodically, we're storing a state, and we're setting the value of a module global variable depending on the current state of the task. Here's another simple example. This is again taken from the ERES2 book. So we have a simple filtering operation here, and again we're carrying out the filtering operation, this time assuming we're using some kind of ADC reading that I assume we get in the lines here. I haven't attempted to include the code for the ADC reading. We're using the current ADC reading and we're performing a simple low-pass filtering operation on those values. So we're storing the storing the current filter settings, reusing those each time the task is released. So I've already mentioned cooperative tasks. What this means, in a little bit more detail, is that we allow the task to decide when to suspend its activities and return control to the scheduler. So the scheduler will only interrupt such a task if it overruns. That is, if the task exceeds its predetermined worst-case execution time. A key part of this is that we're viewing the world in the way that says the task, rather than the scheduler, knows when it's appropriate to suspend its operation. This is, for some people, not the way they're used to working with the world. They're used to working with a real-time operating system, and the real-time operating system interrupts tasks when it wishes to do so. We're taking a slightly different view of the world here, in that as far as possible, if it doesn't generate any problems or unexpected states, we let the task decide when it's appropriate for it to suspend its activities. It's a different way of viewing the world. It can lead to very simple, very deterministic systems. One thing should be noted at this point: the simple scheduler that we introduced in video 2 and is described in chapter 2 of the ERES2 book only has a limited ability to interrupt overrunning tasks. We'll look in several later videos about various techniques we can use to shut down tasks that overrun, and we can do that very precisely. Typically, we can detect a task overrun using some of the techniques we'll work on in later videos. We can detect a task overrun that's 1 or 2 microseconds. When a task overruns by 1 or 2 microseconds from its predetermined worst case execution time. It's important to be clear here that every real-time system relies on worst case execution time information. So we have a particular hardware platform and we have information about the task worst case execution time. These together are the foundations for much of the rest of the design. If the hardware platform is unreliable or our task worst case execution time information is incorrect, it doesn't really much matter what we do with the rest of the design. It's going to be very difficult to create a reliable system. So we'll look at some techniques in later videos that allow us to measure the worst case execution time of our tasks precisely. So let's look at a basic problem that can arise in a TTC design if we don't create our tasks in an appropriate way. We'll look at the problem and then we'll look at a simple solution to that problem. Once you've seen the solution, most people think it looks like common sense, which simply means that it's a good design pattern. So let's look at the problem. Suppose I've got an embedded board and I want to send some information. I'm going to assume I'm going to use a serial link with an RS-232 type connection and probably some kind of USB to serial converter in the link, but I'm going to use a UART connection on my embedded board and I'm going to send a string of characters to my laptop. So this is what I'm going to send. I'm going to use a printf function that is provided by my compiler manufacturer, I'm assuming, and I'm going to use that to send this string of characters to my laptop. My printf function probably looks something like this, where it writes the characters to a buffer within the UART hardware. I'm going to assume that I'll use an RS-232 type link to send data to the laptop, and I'm going to assume that I'll use 9600 baud. That's a low baud rate, and we could reduce some of the problems that we'll discuss in this example if we increase the baud rate. But fundamentally, it's not the baud rate that's the problem. It's the software architecture that we start with. So I'm going to leave it at 9600 baud because it makes it easy to discuss the problem, and we'll take it from this point. So that's the string I want to send. And that's how I'm going to send it. In this case, if I use 9600 baud, it's going to take me about 42 milliseconds to send these data from my embedded board to my laptop. Now my 42 milliseconds is far longer than I have available on a typical design. If I've got a typical TTC type design with 1 millisecond ticks, I can't have a task that takes 42 milliseconds to run. I generally require that my task will complete in less than a millisecond. Even in an aerospace design, I might use 25 millisecond ticks, but in that kind of design, even in that kind of design, I wouldn't want to have a task that took more than 40 milliseconds to complete. I need a slightly better solution. The problem. So I don't want to just try and send my data directly over my UART link to my laptop. Instead, what I'm going to do is I'm going to take my characters and I'm going to copy them to a buffer. That just means I'm going to copy the characters that I want to send to the laptop to an array in memory. Then what I'm going to do is I'm going to schedule a task to send one character from the buffer every 10 milliseconds, for example, to my laptop. So I write these data, it's a very fast operation, and I'm going to schedule a task to send one character from the buffer every 10 milliseconds. Now if you think about the previous version of this system, it took me about 42 milliseconds of CPU time to send these data directly from here to here, because I was essentially sitting and waiting for each character to be sent. So I was waiting for the character to be sent, and I'm basically passing the data to the UART, and I'm sitting there waiting, saying, have you sent it yet? Have you sent it yet? Have you sent it yet? But that's a pretty stupid architecture, fundamentally. What we're doing here is we're passing all the data to a buffer, and then we're scheduling a task that sends the data from that buffer to my laptop. And the key is that we schedule the task at a time interval that's slightly longer than the time it takes for the UART to send a single character to the laptop. If we do that, there's no waiting. And if we do that, then rather than having a 42 millisecond task execution time, our task execution time is very, very short. It takes next to no time to transfer the data to my character buffer, probably a fraction of a millisecond. To transfer my data from the character buffer, one character at a time, to the laptop also takes virtually no CPU time, because the UART buffer that I'm copying the data from here, from the character array to, will be empty. So I don't have to wait for that buffer to be released. I know that if I schedule the task to send the characters at a sufficiently long interval, the UART buffer will be clear by the time I pass it the next character. There's no waiting, and my overall CPU load here is virtually zero. This doesn't just work with RS-232, it works with various other communication protocols. In any situation where we need to take large amounts of data and transfer them out of our system, we can use this kind of architecture. If you want to learn more about this example, please take a look at the ERES2 book. Let's look at another example. So we talked about reading using polling, reading the state of a switch using polling. That's a pretty straightforward process. If we assume that the switch is pressed by a human being, then typically the user is going to press that button and wait for several hundred milliseconds for a response from the system. If the system responds within about 50 milliseconds, as far as most human users are concerned, that's pretty well instantaneous. So somewhere between 20 and 50 milliseconds, and the system response will seem fast to a user. Of course, not all inputs are as slow as that. Some inputs coming into the system occur at a much faster rate and don't originate from human inputs. Let's look at one example. Suppose we've got a rotating shaft and we're measuring flow, using this to measure flow rates through a pipe, liquid flow rates. So we'll assume that this shaft is rotated by the flow of liquid through the pipe. We've got some kind of optical sensor and we get a pulse chain. And the frequency of that pulse chain is related directly to the flow rate through the pipe. Provided we've got fairly low frequencies, up to around 1 kilohertz, then we could still do this activity using polling. But beyond a fairly low frequency, this just becomes impractical. In a real-world design, the waveform would not be perfectly square. We'd see some attenuation of the signal. We would see some changes to the shape of the signal as a result of cable effects, capacitance in the cable, etc. We'd have a filtered version of that waveform. We'd have to decide when we were going to sample the waveform. We'd have to sample at quite a high rate to be comfortable and ensure that we had not missed any pulses. Alternative to using simple software polling is to use a timer counter unit as part of the microcontroller. So here we might have a multi-stage task again that's set to read from the timer counter hardware perhaps every 100 milliseconds. So in this case, what we have is we're taking our pulse input, feeding it into a timer counter unit in our microcontroller. We have no CPU load from this. We effectively have parallel processing. So the timer counter input would carry on operating, counting the pulses that it receives without any intervention from the CPU. And we can typically do this up to very high frequencies. And the frequencies will depend on the particular hardware platform that you're using. But the frequencies you can support will be much higher than we can support using software polling. So we could follow the kind of approach outlined in this slide. For example, read from the timer counter unit every 100 milliseconds, and we'd get a precise measure of the flow rate, regardless of how high that was. If we needed to, we could read from the timer counter unit every 1 millisecond, for example. The task that was required to interact with the timer counter hardware would be very short and would not require any delay code. So what about serial inputs? So we've seen that we can send data out from the system by using an appropriate buffered arrangement to deal with the data transfers. We can do something similar with data that's coming in a similar manner. So we'd use some kind of buffer, perhaps a DMA buffer or a FIFO buffer, to buffer inputs that come in to the system in a similar way. And then we would read periodically from that input buffer. This is fine for dealing with large data transfers, but if you need to respond to events, if an input comes into your system and you need to respond to it very quickly, then this is one of the situations in which you would have to consider whether a TT solution was necessarily the right one for your design. You may need to consider either what we call a quasi-TT solution that we'll look at in a later session, or consider a fully event-triggered solution for your design. Before you do that, we'll look at a couple of other alternatives. But in many cases, again, just as we could with the data outputs, we can deal with data inputs using some form of hardware buffer. So here's an example for an industrial control system, an example of using serial comms for input and output with large messages sent at high bit rates, quite happily using a TT design. So here we might have communications from a PLC unit, programmable logic controller, that's fed into MCU-A in this design. These could be large messages supported by a DMA or a FIFO type buffer, and we could use similar type of arrangements to support the communication, again with large messages between MCU-A and MCU-B. Another option that we can consider is use of multi-core processors. So this kind of configuration, for example, an NXP LPC 54XXX processor has two cores, a Cortex M4 and a Cortex M0 Plus. So we could use the Cortex M0 core to deal with high-frequency serial inputs, if, for example, and use that core to process a small number of interrupt events and then pass the information that's received from those interrupt events into the main processor and run a TT architecture on the main processor. Alternatively, we could configure the system so that we had a fully TT design synchronizing all of the processors. There are a number of different options here. That brings us to the end of this video. Before you watch the next video, please read Chapter 4 in the ERES2 book. Thank you for watching this video.